So I modified the first slide of the notes to something that you guys don't actually have. Hey, did you need to come in? What's up?
Is Driana or Sean here?
Right in.
Can I see you for a sec? Sure. And then Sean after that?
See with you then, sure. Okay, so I changed my first slide here. I threw on 2 diploma questions, one of which you guys should have the skills to solve currently, but the second of which is my goal for the class. I want to show you how to solve the second one by the end of class. So why don't we start by solving the first one, though? The question basically says, if the concentration of H3O plus in sulfuric acid is given to you, can you find the pOH? And for us to be able to do that, I want to just talk quickly about what this would look like as a chemical equation. Sulfuric acid is H2SO4. And we've hopefully learned at some point that when it ionizes in water, it's going to turn into H3O plus. And its conjugate base is the term we'd use now. That would be known as HSO4 minus. Does that work so far? I've also done something very purposeful in the way I've written this one here. Look at the arrow I drew. I didn't draw a double-sided arrow. Why? I think I heard you say it. You said it. Okay, it's a strong acid, yeah. This guy right here is known as a strong acid. And one of the things I want to focus on today now is the strength of acids and bases. But hopefully you know a little bit about strong acids is that they 100% ionize. There pretty much is not an equilibrium system for strong acids. They break into pieces, and they don't return back into the stuff they started with. If they do, it's like 0.001% of the time. So what this means then is we don't really need to make an ice table for strong acids, because whatever concentration you begin with right here, all of it is going to turn into this concentration right here. It should have a 100% yield. If this started as 1.2 times 10 to the minus 5, it would go down by 1.2 times 10 to the minus 5, giving you nothing here. This would go up by 1.2 times 10 to the minus 5, meaning this is 1.2 times 10 to the minus 5. So you don't really need to make an ice table for strong acids. It's fairly straightforward. Now you just need to do your calculations. So I know it's kind of a mess now, but if you have an H3O plus concentration, do you still have some base in the solution? Why? Because now water is an acid and a base, and this is in water, clearly, right? So what you do is you do Kw equals your acid concentration times by your hydroxide concentration. Kw for water, we know this. It's 10 to the minus 14, right? So you'd say 1 times 10 to the minus 14 equals, well, why don't I just save a step here? The OH minus concentration is because you're going to divide that guy down there. So if I divide by 1.2 times 10 to the minus 5, someone help me out here. You got a calculator nearby? I have mine now too. 8.3 repeating to the minus 10. Anybody else got that? Okay, so that means that even though it's actually an acid, you do have some concentration of hydroxide ions. It's pretty minimal though. 8.3 repeating times 10 to the minus 10. Last step though, it actually wants the pOH. How do you find a pH or pOH? What's that formula? Negative log, yeah. So then to get a pOH, you would negative log that number we just found, and that should give us our answer. And I got the answer of 9.07, that's a 9 by the way, 9.07918. I've been hinting at a question like this for a while. Make sure you're very careful on sig digs now. Based on the original question up here, which I've written all over, see how there's only 2 sig digs sitting right there? A common mistake is a student might say the answer is 9.1. Because they'd say this has 2 sig digs, but it doesn't. Because of it being a pH, this 9 right here doesn't count as a sig dig, and so you actually have to make it 9.08. This actually has 2 sig digs. Does that make sense? Okay, that question is one that I think I could have reasonably expected you to solve, because we've already kind of worked with that. But the second question is the one that I want to solve by the end of the day. Let me start off by doing the exact same sort of process with it, and I'll show you where we struggle. This guy right here, HCN is a weak acid. And by virtue of it being a weak acid, not all of the HCN is actually going to turn into the two products. If I tried drawing an ice table in the exact same setup, and I put a 0.20 right here, this is not true. So don't draw this part out, but it would not be true that it goes down by all of 0.20 making 0, and then this one going up by 0.20, and this one by 0.20 making this 0.20. Like, that's not true, because this one actually exists at equilibrium. There is going to be something left over here, and we don't know what that amount left over is going to be. Does that make sense? On yesterday's quiz, or 2 days ago's quiz, I actually gave you a percentage. I actually looked this one up so you can answer the question, and I think it was 0.00498% of the time this stuff will actually turn into that stuff down there. But the issue I need to work with now is they're not going to give you that percentage. They're going to expect you to be able to figure that out by yourselves. So where do we find that information? Today's goal, I really want to focus on this chart and how to use the Ka values along the side to solve a question like this. So I'm going to come back to this question a little bit later, once I maybe cover a few more topics. But to me, this is kind of the linchpin lesson of the whole unit. We've talked about equilibrium a little bit on its own, and how to do ice tables. We've also talked about how to do acids and bases, but for the most part, it's either been either equilibrium or acids and bases. Today, we want to talk about the equilibrium of acids and bases and kind of put the whole thing together now. So, okay, so let's start with my notes here. I've already introduced to you guys the concept of a Kc value. Kc value is essentially an equilibrium constant. It's a value that's always the same. The only way you can change this constant is by changing the temperature. You guys recall that from yesterday? That's the only way you can change a Kc value. Once you've determined it, it's temperature dependent, but that is a constant. So there's one constant you should have memorized, and that's water's. We call it Kw. Water's constant is 1 times 10 to the minus 14. Essentially meaning that water has the ability to turn into H3O and OH minus, but since it's such a small Kc value, it really does it very rarely. Okay? And rather than call it Kc, we call it Kw. Today we're going to talk about Ka, and like I said, I've been hinting at this for quite a while. Ka just refers to it for an acid. We're also going to talk about Kb. Kb is going to be something that is for a base. Fair enough? So, we give it its own unique name and symbol, so today is Ka. Let's talk about the first 6 then. The very first 6 acids that we have on the table here, they're considered strong. They don't actually ionize at an equilibrium kind of concept. They basically react nearly 100% of the time. So we don't actually need to do much equilibrium with them. They do not even have a Ka value. If you look at these top 6 acids right here, the Ka value is just called very large. The reason why it's very large is that it's very product forming. Okay? The larger the K value, the more products you form. Does that make sense? Well, it essentially forms all products and no reactants. So it's so large that we really can't even measure it because there's no reactants left to measure. Essentially what this means then is that H3O plus, I missed the plus sign right here. H3O plus is kind of considered to be the strongest acid possible. Here's the reasoning why. If HCl reacts with water, that's gross, forms Cl minus and H3O plus, but it does it all of the time, HCl is always, oh my goodness, I can't draw today. Let's try this again. Okay, HCl is going to react with water. It's going to form Cl minus and H3O plus. But since it happens all of the time, essentially if you have HCl, you have entirely H3O plus. So what I'm trying to say here is that there is no acid stronger than H3O plus because any acid that is stronger than H3O plus is just going to turn into H3O plus. That was wordy. Did that make sense though? Long story short, if you look at the table right here, one thing I haven't talked about is this little gray bar right here. See how there's a bar for hydronium right there? We usually consider hydronium to be the strongest acid. The reason being is that any of the 4 things that are above hydronium are going to 100% turn into hydronium. Does that make sense? So essentially all 7 of these top things mean the exact same thing. They all mean you're going to have H3O plus pure H3O plus, nothing else, because the top 6, that's what they turn into 100% of the time. Nearly 100%. Does that work? Well, here's an example of not a strong acid. HF, hydrofluoric acid. You might recognize hydrofluoric from pop culture. Anybody know what I'm referring to? Breaking Bad? Anybody watch Breaking Bad? Who's watched Breaking Bad? Okay. In the first couple episodes of Breaking Bad, if you've watched the show, Walter White needs to dispose of a body. And in order to do so, he uses hydrofluoric acid to basically dissolve the dead corpses. And Jesse doesn't use the polyethylene container. He just puts it in the bathtub. And like hydrofluoric acid will like eat through the bathtub. Yeah. But it won't eat through plastics though. So, anyways, I want to talk about the difference though between corrosive and strong. Strong means that it 100% ionizes. But that's different than how dangerous it is. Hydrofluoric might be the most dangerous acid out there, but it's actually not strong. Does that make sense? There's a difference between the two. So this is highly corrosive, very hazardous to your health, but it does not ionize 100% of the time. Okay? And so what we can do is we can write an equilibrium expression stating that HF will react with water, making your H3O and your F minus. But this number right here it's usually less than 50%. And that's not the less than sign, is it? Let's do it that way. So it's a less than sign. Okay. Our goal today is to try to figure out how that percentage actually works. How much of it actually does change from reactants into products. Well, one of the things that's a given to you now in your data table is they're going to give you a Ka value. So can you guys find the Ka value for HF? Just locate where it is. Yeah, it's 6.3 times 10 to the minus 4. What does that mean? Does it mean it's products or reactants favored? Well, it means it's reactants favored, right? It's a small number. However, in terms of ranking, where does it fit on the ranking of acids? And I'd say, well, it's actually fairly high up. Like, it's still technically a weak acid, but comparatively, it is one of the stronger weak acids. Does that make sense? So that's what one of the things Ka and Kc values are useful for, is it can help you to compare. Okay. The other thing that it's useful for is it can help us work backwards to solve a problem. And I'm going to hopefully have an example of that coming up soon here. Okay, here's one more slide, just a quick reminders of terms. I was trying to allude to this a bit with the Walter White hydrofluoric acid being dangerous thing. Strong and weak are different than concentrated and dilute. Concentrated is when you have a lot of it. Dilute is where it's dissolved in a lot of water. Those are different than strong and weak. You guys have heard these words before? Okay. Wait, let's hop to an example here. Here's an example. Let's say that you have the pH of a 1.00 moles per liter solution of acetic acid, and you calculate it to be 2.38. Let's try calculating its Ka. Let's try to calculate the Ka value and see whether we get the same thing essentially as what the data book claims it should be. By the way, this is what we're going to do in our lab. When we do our lab next week, Tuesday, it's going to be exactly like this. We're going to calculate a concentration. We're going to use a pH meter, and it's going to give us a Ka value. And then if our lab is successful, we're going to look in our data booklet and see is the Ka value the same thing as the book claims it should be. So, okay, so let's walk you through your first example. What's acetic acid? What's its formula? Okay, whoever said that. CH3COOH is acetic. What is acetic going to do? Well, it's going to attempt to try to ionize itself with water. So we're going to add some water. We already probably know by a really educated guess this is probably at equilibrium because it's not one of the strong acids. So I'll write a double-sided arrow. And it's going to make what's called a conjugate acid and a conjugate base. The conjugate base is going to be CH3COO negative. That's going to be this guy right here. It's going to be his conjugate base. And it's also going to make a conjugate acid, which is going to be H3O plus. Right. Earlier today, I was really lazy with writing things out, and you shouldn't be lazy. I've been harping on this for you for probably a year and a half now. You should always write your states of matter. And this is another good reason as to why they're important. So this guy's state of matter will be aqueous. This one's state of matter will be aqueous. This one's state of matter will be aqueous. But this is where this is actually a really, really important point today. What's the state of matter for water? Liquid, yeah. And that really impacts us in terms of how we do our calculations. Because the rules for equilibrium are, if it has a variable concentration like a gas or an aqueous, we can use that. But liquids do not have variable concentrations. So whenever we try to do calculations involving liquids, in this particular example here, we have to omit them entirely. We actually have to leave out the liquid. And I want to go back to a slide that I skipped over here real quick. It's this guy right here. I didn't point this out yet, but look at the Ka. Here's the product written down here. Here's one of the reactants written down here. Why didn't we write water? Because it's a liquid, so we can't count it. Does that make sense? So when we write out an expression, it's actually really important that we don't count the liquids. Hey, Rob. All right, let's start filling out our ice table a little bit here. Yeah, sure. It says that we start with a 1.00 mole per liter solution of acetic acid. Well, that would go right here. This is 1.00 moles per liter. Is all of this acetic acid going to turn into these two guys over here? No, in fact, very little of it will at all, right? We're expecting that it's going to happen so rarely that it's difficult for us to measure. So one of our issues then is trying to figure out, well, what other numbers do we have? I mean, I didn't give you any other numbers, did I? Well, okay, I gave you one other number. But, like, where do you... Oh, actually, that's true. That's a good point. We can put these guys as 0. Good catch. Okay, but in terms of the other numbers I gave you, this 238, does that belong on the table somewhere? Well, first of all, it's a pH value. So, I mean, this doesn't account for pH. But, wait, hang on. We can use a formula to convert pH into something else, right? If you use the formula 10 to the minus pH, that'll give you an H3O plus concentration. So 10 to the minus 2.38 will give us 0.00416686, blah, blah, blah. So we weren't given a concentration, but we were given a pH. How's that helpful? Where on the table does that go? Yeah, it goes under the H3O at the equilibrium concentration, right? Because we didn't start with any of this, but eventually we end up with 0.004. Sorry, that is a 1.6, by the way, 416. That should be enough for right now for Sigdigs. Okay, well, based on your knowledge of how a table works, that means this one should have gone up by 0.00416. This one should go up by 0.00416. This should be 0.00416. Water, I put a line through the entire column. You cannot do anything with water because water doesn't have a concentration in this sort of capacity. Okay, this one is going to go down by 0.00416. And it's at this point here that I need to explain to you a really important Sigdig concept. Many people would try to do this, 1 minus 0.00416, and they would try to make this number be 0.99584. And that's actually incorrect. So if you kind of hopped ahead a little bit, there's actually an error there based on Sigdigs. Right here, you're adding and subtracting. And the rules for adding and subtracting with Sigdigs is that you have to cut things off at the smallest precision you have. This number right here, I have lots of digits for. That's fine. But this number right here only goes to the nearest hundredth. So this number right here, when I add and subtract them, it has to also get cut off at the nearest hundredth. Yeah, actually what ends up happening is this will actually stay at 1.00. It's a very kind of odd scenario to come up here, but essentially what's happening is you have 1.00 and you're minusing almost nothing. I want to give an analogy again here that maybe will help. This guy right here, imagine that he has $1 million. And out of those $1 million, he has to donate $4.16 to these guys over here. Now, to these guys over here who have literally nothing, $4.16 is a lot. Does that make sense? It's a world of difference to them because they used to have nothing, and now they actually have something. They've gone up. I mean, you can't even figure out how many times they've gone up because going from 0 to something is like infinitely increasing what you have. Does that make sense? However, for the guy who has $1 million, going down by $4.16, it's like a rounding error. You wouldn't even notice the difference. Does that make sense? So based on the way that SIGDIGs would work right here, you actually won't even lose anything. You'd actually leave this at 1.00. Does that make sense? So then to find your Ka value will be your conjugate base, the CH3COO negative. It'll be your H3O plus, and it will be your original CH3COOH, because we're not counting water, because water is not because water is a liquid, right? It has no concentration. So this guy right here, I'm going to make 0.00416 repeating, whatever it is. Since it's twice there, would it be okay if I just squared that number? Because we're using 2 of them. But essentially we have to divide by 1. Right? Because this guy's concentration over here doesn't effectively change. It basically doesn't register. So take the number that you have of that 0.00416 number, square it, and that should be our Ka value. I got 1.7378 times 10 to the minus 5. Yeah. Having a hard day already, bro.
Would you be having us rounded off when we added, or would we use the exact value?
Like the 1.00 there?
Yeah.
You should round it off there. Because essentially what's happening here is that, I mean, this number right here, we don't want to round this number just yet. But because of the fact that we have this adding calculation that's going on right here, recognize the fact that when you subtract this number right here, like these SIGDIGs work differently than the rest of them do. So I mean, now that we're done, we should go back to our SIGDIG rules for the multiply divide type stuff and say how many SIGDIGs do we get. And I'd say this gives you 3 SIGDIGs, but this one right here gives you 2. Yeah. So then use that for 2. So I would say this is 1.7 times 10 to the minus 5. So yeah, in that first ICE column, in that first column, you always have to kind of play that one a little bit differently because of the way that it adds and subtracts. Does that make sense? Like the rules for that apply differently. Okay, to find the Kc value or the Ka value in data booklet now. How does it compare? Where's acetic acid?
1.8.
Okay, so 1.8 times 10 to the minus 5. So if this was our lab that we're going to do on Tuesday, we're pretty close to the accepted value. Now, I mean, this will depend on the accuracy of your measurements. So the 2 measurements that are going to matter for us, we're going to need to calculate this moles per liter, and we're going to need to calculate this pH right here. Calculating a pH is actually really easy. You take the pH meter, you put it in the thing, and it tells you what the pH is. Only if you guys have any experience at all with my pH meters. So here's the cool thing though, I bought some new ones. So we're going to try some fresh and calibrated ones, and hope they're going to work. Like they're brand new out of the box. So hopefully that'll work. How do you calculate a concentration? That's a good lab question for you. How do you do a concentration in a lab? Okay.
What you measure of your product, your reactants, say if you were doing like water stuff, you measure water.
Okay, and I think that's what you're kind of illustrating
Yeah.
here. One of the options is you make it yourself.
Yeah.
Okay, that is one option. There is another option. What if you can't make it yourself? What if it's already store-bought in a container and it claims that it's about 1 mole per liter? That's what we're going to do. Yeah. So next week, Tuesday, what we're going to do is we're going to do a titration to calculate the concentration, confirm what it is. Then we're going to stick the pH probe into it, and hopefully it's accurate. We'll see how accurate it is. And by doing a calculation like this, we'll test and see whether the Ka value is actually what it claims it should be. That makes sense? Yeah, one more titration. So, did that first example make sense? Okay, now that one's actually not very useful because, truth be told, now that we have a whole bunch of Ka values, they're all actually listed in your data booklet for you. So the more common issue is actually, I'm going to give you a concentration and ask you to predict the pH. And that's what's happening right here in this first example that I pulled off the old diploma. See how this example right here, all I give you is the starting amount, and I don't give you the pH. So this is going to be working backwards. Now that we know what the Ka value is because we have it in our book, and I give you the initial concentration, we're going to solve for the third variable of the pH. Hopefully I have one of those in my notes here. Before we do that, though, why don't I have you guys try doing this one here? This is exactly what we just did. Why don't you guys try doing one of these on your own? See if you can do that. So, I mean, you should be able to tell me the Ka values by looking at it in your data booklet, but let's pretend it's a lab. Let's see whether we can actually calculate this based on some values, see whether this is true. What's up?
Subtracting, because this was to the negative.
Okay, so what did you get to the negative 4?
3.3113.
Okay, so when you get to this column here where it's 0.25, it's going down by, what was the number?
3.3113 to the negative 4.
Okay, so if I were to write that out, this is 0.25, and it's 0.0003313. Will that make a dent in the 0.025? No. Right? It's that rich guy giving up a couple dollars. Right? Like, he's got $250,000 and he's giving away $3.31. He won't notice. Makes a huge difference to the guy who has nothing, though. I filled out the ICE table for anyone who hasn't gotten that far yet. Basically, what you have to do is take your pH value and 10 to the negative or 10 to the minus pH to get your concentration. That concentration you have to write like 5 times on the table. It's kind of annoying. You have to write it pretty much everywhere over there. That's what it went up by. If you didn't hear my conversation with Taylor, though, if you take 0.25 and try subtracting 3.3 times 10 to the minus 4, it's essentially it does nothing. Right? Because 3.3 times 10 to the minus 4 is 0.00003. You know, like, so basically that number in the E column for H2CO3 is still 0.25. Like, it does not actually effectively change it at all. So if you got this far, the last step then to find your Ka value would be to take 3.311 E minus 4. We're going to square it because there's 2 of these guys over here, and we'll divide by 0.25. I calculated 4.4 times 10 to the minus 7. That only gets 2 sig digs. And you'll notice that in your data booklet, all of the Ka values typically only get 2 sig digs. And probably the biggest reason why is that the pH that you use to start only gets 2 sig digs. It's really hard to measure a pH past this digit. Does that make sense? Like, the 3, since it doesn't count for a sig dig, is no good to us. A pH meter usually only gets to the nearest hundredth of a pH. So it means that most of the time you're limited to 2 sig digs. So. Anybody else get this value as well? Okay. How does it compare? 4.5? 4.4. Okay, so it's pretty darn close. That makes sense? Is that something you guys can replicate? Okay, so let's find the other type of example then. So why don't we skip this one here since you guys have the hang of it. This is the exact same concept. I give you a pH, right? I give you a pH, I give you a concentration, find the Ka. That's the exact same thing. So let's move past that one. Let's do this one. This one is backwards. I only gave you one number. I gave you a concentration, and that is it. And now this time I'm actually asking you, tell me the pH. So rather than giving you a pH and a concentration, I just give you a concentration, say we're trying to find the pH. The twist to this question here is that you have hidden information. The question doesn't specifically spell it out for you, but if it tells you that it's methanoic acid, you actually should now know the Ka value. Because you can go look it up, right? So the Ka value is... I cannot find it.
It's under forward test.
Oh, there you go.
Oh, there you go. Okay, so 4 above the page break. 1.8 times 10 to the minus 4. What are the units for Ka? Good. Yeah, there are 2. Okay, so here's how you'd solve this one. And we've actually done this before. I've been prepping you for this very moment. We're going to use x's as part of our solving this thing. Yeah. So first start by writing out the equation. So our equation is methanoic acid, HCOOH. We're adding it to water, which, by the way, that's really not going to make any difference. So we can almost skip it. Is going to be at equilibrium, which H3O plus, and with COOH. It's actually probably it'll probably work like that. And that'll be a minus. So in terms of what we get to know, all we get to know in our ice column is this top number. That's the only number we know. This is 0.200 moles per liter. From a practical point of view, how are we going to know that concentration? 2 ways. Either we will have made it ourselves, or it will have been titrated. That's the way that we will know that starting number. Does that make sense? Based on this, we should be able to assume that, okay, there's 0 of the product starting. But that's all we've got to go with. So we're going to fill up the rest of the table with x's. This guy is going to go up by x. This guy is going to go up by x, meaning that these guys are going to have an x value. Well, the HCOOH is supposed to go down by x. Here's the thing, though. We just covered this a few minutes in previous questions here. What's pretty typically going to happen in this column here when you try to subtract this amount? We don't know what the amount is, but what should happen is nothing should happen. And I want to show you why this makes a huge difference in terms of how you solve. So for right now, can we write it like this? And then in a second, I'll show you why we're going to change that. But ideally, this is supposed to go down by a certain amount. Well, when we write out the equation, then it's going to be Ka equals x squared over 0.20 minus x. But we know the Ka. It's 1.8 times 10 to the minus 4? 5? 4? This is a quadratic. So the way you'd have to solve it would be to either use the quadratic formula, type it in your graphing calculator, find where it crosses. Less if, but still not great. But here's the twist. This is what makes this question quite nice, actually. Yeah. Because of the fact that we've already kind of seen in a few examples that the amount that this guy right here is going to lose is so minimal. And we know that because what's our Ka value? It's 10 to the minus 4, right? Does a 10 to the minus 4 produce a lot of products? No, not a lot at all. I would expect, if I had to guess, that it's going to make like 0.0000597 moles per liter, right? Like it's not going to produce a lot of products. So we can assume that when this goes down by x right here, that the minusing x really doesn't do anything. And that one little twist makes all the difference here in terms of making it easier to solve. Because now that that is no longer there, there's actually a much easier way of solving it. All you have to do now is take this number, times it up to the other side, and square root. You guys visualize that? Let me rewrite it again here. So what you would do is you would take x squared, you'd make it equal to 1.8 times 10 to the minus 4. You'd times it by 0.200. So you're swinging that guy up there. And then just square root both sides. I got 0.006. Hello. Anybody want breakfast? Do you guys have yogurt?
Yep.
I'll take one. Anybody else? Okay. Did that make sense? Okay. If you look on the data table here, there's actually a little star note down at the very, very bottom. Can you guys see that at the very bottom there? I want to talk about this. It says here there's an approximation that can be used instead of the quadratic formula. Okay. You know how I mentioned a few seconds ago here? If there was an x sitting right here, if that was sitting right there, you'd probably have to use the quadratic formula. This thing actually points out you can use an approximation instead of the quadratic formula. It basically says if the concentration of H3O plus produced is less than 5% of the original acid concentration, we can use the approximation essentially. It's really wordy, but long story short, what it's saying here is that so long as the this number right here, so long as we can assume that this number here is so small that it doesn't really matter, then we can, you know, that minus x right there, it's saying you can get rid of that. That makes sense? Generally, the rule of thumb is what you have to do is you have to take your Ka value, times it by 1,000. So if you take your Ka value of 1.8 times 10 to the minus 4, if you times it by 1,000, I get 0.18. If you take your Ka and times by 1,000. Yeah, see how it kind of says that in the little blurb there, times by 1,000? If this initial concentration is still more than that, you're allowed to use the approximation. So is this amount more than 1,000 times your Ka? Yeah, I mean, not by a lot, but it is. So the approximation is considered to be valid. Okay.
Why is it okay if it's larger? When it wants to be smaller?
Basically, because what it means is that this number right here is still, like, we want this number to be very small.
Yeah.
Because if this number is small, it means that you don't make much of this, right? So if this number is small, if you times it by 1,000 and make it a little bit bigger, and it is still less than this amount right here, then it doesn't make much of a difference.
Okay, I get it now.
Okay. Now, technically, if you actually do the math backwards here, now that we know what x is, I got, what was it, 0.006? If I were to actually put in 0.006 right here, would it have made a difference? Actually, yeah, it would have. Right. Look, this, if you line it all up, it would have. Okay. But the rules for what we say on the diploma are we're allowed to approximate. So although technically we know we're wrong, we're doing this as a time saver so that you can avoid using the quadratic formula. Does that work? So long story short, we're always going to do this sort of method where we just don't subtract x. All you have to do is one quick test. Take the Ka value, times it by 1,000. If timesing it by 1,000 is still smaller than this initial amount here, you can do this whole little cheating skip result thing. Okay, so last part here, it actually wants you to find the pH. How do you find a pH if you know a concentration? Negative log, yeah. So let's take that value we just calculated, which is an H3O plus value, and let's negative log the thing. I got a pH of 2.22, 1.8. And based on our sig digs, this guy right here has 3 sig digs. So you might be inclined to think, great, I get 3 sig digs. But no. The Ka value in your data booklet comes with 2. And that's really, really mean because you might not notice that, but all of your Ka values come with 2 sig digs. So you only get to keep 2 sig digs, which means, again, you got to really be careful on sig dig rules. The answer is actually 2.22 because as a pH value, this is actually what has 2 sig digs. It looks like 3, but it only has 2. Be oh so careful on these. That makes sense? Okay, why don't I go back and do that first diploma question, and then let's take a 5-minute break, because I still have more after this, obviously. So if you guys want to write this one down, this is an old diploma question. We should now have the skills to solve it, I hope. Really, all you're going to be given is an equation and a single concentration. These are frustrating to look at because all you get is this number right here. That's it. Okay, first thing, I want to show you what not to do. Some students, when they look at this question, if they've forgotten this whole really big lesson, they think, oh, how do you find a pH? You negative log. And so they go negative log of 0.20, and they tell me that's the answer. And they take a question which is actually really complicated, and they make it way, way too simple. And the problem with that, though, is that exactly, this is the 0.20 right here, but we actually require this value down here to negative log. So please don't do that. Okay, so let's write it up from the top again. HCN, H2O, CN, H3O plus. Once you do a few of these, though, they fit the exact same format every single time. This is a 0.20. This column, don't care about. It's a liquid, it's water. This guy's got nothing. It's going to go up by an unknown X amount. Think of it as being a guy who's dead broke. He gets something. To him, whatever he goes up by is huge. If you're a beggar sitting on the side of the street who has nothing, and a guy gives you $3.12, that's a lot. Right? But over here, if you're the guy who has $200 million, I know it's not to the same scale, but if you have lots of money, and you give someone $3, it doesn't make a difference to you. Now, before I actually do that approximation, I should do one quick test. I should find the Ka value for HCN and times it by 1,000, just to make sure. So the Ka value for HCN in your data booklet is times 10 to the minus 10. I don't even think I need to do that. If I take something to the minus 10 and times it by 1,000, it'll now be to the minus 7. That's way lower than this number, right? So last step here. Your Ka value will be equal to x squared from these two x's right here over 0.20. We know the Ka value because I just looked it up. I forgot it already. 6.2 times 10 to the minus 10. Swing that guy to the other side. Square root it. I feel like I'm doing a square dance here. Swing your partner square root. All right, 6.2 times 10 to the power minus 10. Times by 0.2, square root the whole shebang. I have an answer for x of 1.11355 or so. Make sense? Okay, we're not quite done though. That number is a concentration, because if you look back, X has been defined as whatever the hydronium goes up by. It's also what the CN goes up by as well, but it's what the hydronium is. So that's the number that we negative log. Yeah, negative log that number. So don't like negative log the 0.2. Negative log that number. I got 4.95. I don't like to give you a hard and fast rule, but I can almost always guarantee you this is going to have 2 sig digs. The reason why? The Ka value out of your data booklet has 2 sig digs. I'd be surprised if somehow you only had 1 sig dig. I guess it's possible that you can only have 1 sig dig, but you're probably having 2. So this will be 4.95. There's your pH. Hopefully you can see why that's a challenging question. Year after year, I look at the stats on questions like these. Sometimes the province's average is like 18% of the province gets that question right. I imagine it's because so many kids, they've forgotten and they just straight up negative log the concentration. They just go straight to that. Right? But there's actually a lot more work here. The other main twist that you got to remember is that it does not give you all of the information in the question. Technically, there's information in your data booklet, which kids maybe forget about. And the other thing they might get confused about is they might forget about that whole minus X thing, about how you're allowed to get rid of it. So if you ever forget, there's that little blurb in the bottom here. It basically says you can skip the whole quadratic thing if you times your Ka by 1,000, and it still is not very large. So, that makes sense? Okay, why don't you guys take a break, because I've been talking for almost an hour. When you come back, we'll finish up what we haven't done yet. Okay, so one last topic here. There's a few more slides left I need to cover. And before I do that section, let me just make sure, does everybody feel fairly comfortable with the questions that we just learned how to solve? Because there is one more example if you want to do it. I feel like I've done 2, but if you want to do this one later, maybe on your own time and call me over, you can try this one. It's almost the exact same as the one we just did, though. It's 0.500 moles per liter, and it's hydrocyanic acid. It's the same one we just did. So if you want to, you can try that one. But you guys feel okay to move on? Okay. Okay, let me introduce reintroduce one more concept that we've talked about here. I need to link this back to the new definitions of acids and bases. So a quick recap of a few lessons ago. According to a guy named Arrhenius was trying to define acids, and here's how he concluded. He said that if you can write it like this, HCl plus water makes H3O plus Cl minus, his conclusion was if you get a Cl minus, this is what makes something an acid. That was Arrhenius' conclusion. And truth be told, that was a great conclusion. It worked out well for lots of different acids. But Arrhenius had a major flaw in his system. And this would be a good example of one of his flaws. If I gave you NaHSO4. The way that Arrhenius would have figured this out is he would have first dissociated and turned it into Na plus and HSO4 minus. He would have then said, I haven't proven this is an acid or a base yet. So then he'd say, I'm going to keep trying. He would then take the HSO4 minus, he would add water to it, and he would find a way to turn into H3O plus by making SO4 2 negative. He would then say, SO4 2 negative? Yeah, that's a thing. So he would then claim that means that this is an acid, which means that reversing your train of thought must mean this guy's an acid. However, his flaw then comes in if he tries to do the exact same thing. He can also prove that it is a base. Because this is a valid molecule, and so then he's also proved that it's a base. Do you guys recall talking about this issue? Okay. We're finally going to resolve it. We actually have enough skills and enough information to do it. There's actually a really complicated formula on one of your following slides. But before I get to that formula, I want to introduce the new theory. The new theory was called Bronsted-Lowry. Okay. Arrhenius defined things as an acid based on what it produces. If it produces H3O plus, he thought it was an acid. Bronsted-Lowry have a really elegant concept about how it's really more about proton transfer. And I actually like this theory not only because it helps solve this conundrum I'm about to explain here, but because it's similar to electrochem. Electrochem is about gaining and losing electrons. Acids and bases look like they're about gaining and losing protons. I mean, that fits, doesn't it? Like, it's so elegant the way it works. Right? Bronsted-Lowry would define this guy as an acid because he is giving his proton to this guy right here. And Bronsted-Lowry would define this guy as a base because he is accepting a proton. A guy who gives is an acid. A guy who accepts is a base. You guys so good with that so far? Well, here's the proof then for how to figure out this conundrum of who is an acid or who's a base. And it really comes back to knowing about equilibrium. Once we realize that what's actually occurring here is an equilibrium system, how do I want to phrase this here? This guy right here would be an acid donating his proton to this guy who's a base, which would make this guy an acid and this guy a base, and they're going to go back and forth in an infinite equilibrium system, which means that this guy right here has a Ka equation. So far, so good? But alternately, I could consider this guy to be a base, someone who is accepting a proton from this guy as an acid, where the proton's going this direction, which then makes this guy the conjugate acid and that guy the conjugate base. Well, here, this guy would in theory have what's called a Kb value, because he's a base, right? I mean, if you can do a K value for an acid, you should be able to do a K value for a base as well. Let me see that I can do the proof myself without screwing it up, and then I'll show you the one on the page there. The Ka value for H2SO4 then would be H3O plus times by SO4 2 minus divided by HSO4 negative. That's what the Ka value would be. The Kb value for the following equation would be really similar. It would be H2SO4 times by OH minus divided by HSO4. That makes sense? Trying to remember how to do this properly now. Oh, I don't think I can do the proof without memorizing it. Okay. Let me just go to the slide here. Yeah, this is the really complicated one. I can remember how to do it myself. Should have looked it up first. This is a similar sort of concept here, only rather than doing it for the acid I just did here, I'm going to do it for acetic acid. Do you guys see how acetic acid right here is in equilibrium with water? And here's a Ka value. What I've done in the following equation here is we found a Kb value for the acetate ion. And what someone really clever managed to figure out is if you take your Ka value and a Kb value and times them by each other, look what happens. See how this guy right here cancels and this one right here cancels? What's left over? Well, what's left over is an H3O plus and an OH minus. And then I asked this question here, doesn't H3O plus and OH minus look familiar? It's KW, right? So this actually led to someone discovering a really clever new formula. So you know how I've been adding some new formulas to your list? Here's a new one. Is that on the next page? Yeah, here's the new formula. We've actually discovered that the Kw value is actually equal to a Ka value for something being an acid times by a Kb value for something being a base. Which, doesn't that make intuitive sense? Don't acids and bases combine to give you water? And this was actually the key for figuring out the whole is something an acid or a base kind of issue. I want to go back to where I did not do very well here. But here's a Ka value, here's a Kb value. We're trying to figure out which of these two equations is going to occur. Is this guy going to be an acid or be a base? Because only one actually happens. They don't both happen. One or the other occurs. And the way we figure it out is by comparing their Ka to Kb value. Whoever has the larger value, that's the one that predominates. Because remember how a Ka value is a way of like comparing how much products it makes? Well, if I have a Ka value of 10 to the minus 1 and a Kb value of 10 to the minus 13, one of those is drastically better than the other one, right? So pick the one that's stronger. So the way we solve this conundrum is we find the Ka value, we find the Kb value, and we just see which one's better. Whichever one's better, that was the way that we can figure out which one's an acid or a base. Does that make sense? So it's actually really easy to find a Ka value. You have a data booklet that lists them all. Does that make sense? Well, that's where this new little proof and formula comes in here. If you have a Ka value, you should also be able to find a Kb value. And so to figure out which one predominates, you just have to compare the Ka and Kb values to each other. So let me show you a couple examples of questions along these lines. So first, let's do some just calculating Kbs to start with. Sodium benzoate apparently has a base. Let's find a Kb for the weak base. What's sodium benzoate? Na is sodium. Anybody know what a benzoate is? Is it on your, is it one of the polyatomics on the top of your table there? Okay, so that's a sodium benzoate. It claims it forms a basic solution. Let me prove to you how it does that. To form a basic solution, first of all, is this guy ionic or covalently bonded? Ionic. What do ionic things do? They split up into their two pieces. So it splits up into Na plus and C6H5 COO minus. Have we transferred a proton yet? I don't think so. So according to Bronsted-Lowry, it's not an acid or base yet. Also, if we use the Arrhenius theory, have we made either H3O plus or OH minus yet? Okay. So let's keep doing what Arrhenius would have done. Let's take this guy down here. Let's do another reaction. Oh my goodness, what's wrong here? C6H5 COO minus. Let's try adding it to water. Could we transfer a proton one way or the other? Which way could we transfer a proton? To the benzoate, yeah. You could take a proton off of your water, attach it to that guy right there. Hey, Devin, while you're by the door, can you close that? Thanks. you could take a proton off your water, attach it to this guy right here. It would make it a C6H5COOH. That should look familiar. That's a carboxylic acid. And you should have an OH minus left over. And according to both definitions that we've learned now, according to Arrhenius, this guy's a base. Why is it a base? Because that produced OH minus. According to Bronson and Lowry, this guy's a base because it accepted a proton. Well, if I want to calculate its Kb value as a base, because this guy is, hopefully now we've clearly proven it's a base, how can I find its Kb value? Well, we now know a formula. Sorry, I'm going to move down to the next section here. Ka times Kb is equal to Kw. So to find a Kb value, take your Kw and times by Ka. So then here's the question then. Where do I find the Ka value? But more specifically, I have to find the Ka of its conjugate acid. Who is this guy's conjugate acid? Benzoic acid. So we actually have to look for this guy over here. We have to look for his conjugate acid. So you need to find benzoic acid in here. It's right below the page break. It's 6.3 × 10⁻⁵. So that means if you want to find out how good this guy is as a base, take 1.0 × 10⁻14 and divide it by this guy right here, his Ka value. What did I say? It was 6.3? I got 1.6 times 10 to the minus 10. Makes sense? Okay, let's try another example here of just calculating a Kb, just so we practice how to calculate them. Let's try doing it for ammonia. So let's just go through the process of trying to prove how ammonia is a base. Ammonia is NH3. Ionic or covalent? Covalently bonded. There's no ionic pieces I can separate this thing into. So unlike the last example, I'm just going to have to go straight to adding this thing to water. Okay, well, can I move a proton one way or the other? Yeah, you can move the proton from water to NH3, right? It would make NH4 plus, and it would make OH minus. So according to both definitions, actually, this is a base. This guy's a base because it produces OH minus. It's also a base because it can accept a proton. How do you calculate its Kb value? Well, Kb is equal to water divided by its conjugate acid. So that's 1 times 10 to the minus 14. Yeah, so you need to look up where NH4 is in the data booklet, which is like way at the bottom. Ammonium as an acid can turn back into NH3. By the way, I should point that out. You guys remember how there's like two columns to this thing here? If you find NH4 right down here, what will NH4 turn into? It will turn into NH3. Essentially, that's the backward side of the equilibrium. That's where the NH4 becomes the NH3. So you need to divide by 5.6 times 10 to the minus 10. Uh, 1.8 to the minus 5. Anybody else calculate that? Hopefully you'd agree. Calculating a Kb value, actually, using this new formula is actually really easy, right? It's just 2 steps. So now let's actually solve one of these questions. Let's figure out whether something is an acid or a base by comparing, which would be my last set of notes here about the amphiprotic. Do you guys remember the term amphiprotic or amphoteric? These are those things that can act as an acid or a base. The example that I gave you a few slides back where I was trying to do this myself is this guy right here. This guy would be considered amphiprotic or amphoteric is the word we used, because it could be an acid or a base. Our question is trying to figure out which one is it going to be. Does that make sense? So to figure it out, we compare Ka and Kb. So here's my question. Which reaction is going to predominate with an NaHSO3? Is it going to be acidic or basic? This 3, by the way, somehow got put as a superscript. It should have been a subscript. Yeah, that screwed up there. So basically my question is, prove to me whether it's an acid or a base. So let's go through the really long process. You guys won't do this every time, but let's go through the long way of doing it first. So start with NaHSO3. Is that ionic or covalent? Hopefully you'd say it's ionic. So you would separate it by dissociating it into these little pieces here. Have I proved that it's an acid or a base yet? According to Arrhenius or Bronsted-Lowry, I'd say no. So I would then take the HSO3 negative. I would try adding it to water. And I can actually do two things with it. I can turn it into SO3 2 negative and hydronium, thereby proving it's an acid. But it reacts both ways. It is also capable of accepting the proton from the water, in which case it would become H2SO3 and OH minus. You guys see how we have a major issue here? So this is where the new Bronsted-Lowry theory and that formula I gave you a few slides ago is actually really clever. We're going to find this guy's Ka value. We're going to find this guy's Kb value. And we're going to see which one wins. Whichever one is a stronger value, that's how we'll know. So for the top equation, it's actually really easy. To find the Ka value for HSO3 negative, I've got a book. Find it. HSO3 negative is about halfway through the bottom half of the table. It's got a Ka value of, just lost it again, there it is, 6.3 times 10 to the minus 8. Is it a good acid? Not really. It's weak, and of the weak acid, it's one of the weaker weak acids. So I'm not liking the shots of this thing being an acid. But I gotta test it as a base as well. But to test it as a base, I have to use that new formula, Kw equals Ka times Kb. So Kb is equal to Kw divided by Ka. So I just have to do a quick division and figure out which one's stronger. Here's the problem though. A lot of kids will screw this up because they'll do this calculation. So don't do what I'm about to do here, just watch. Don't do 1 times 10 to the minus 14 divided by 6.3 times 10 to the minus 8. Don't use this Ka value. Because in this example right here, this guy is the base, and this guy right here is the acid that we're talking about. So you have to use this guy's Ka value. Does that make sense? So the Ka value that we're going to divide by is not the one that we just looked up for the HSO3, but it's actually for the H2SO3. That's the one we have to look up, the one that's actually on the product side. Yeah. So one more thought here about amphiprotic stuff. Amphiprotic stuff should be in both columns. See how I can find the HSO3 right about here? You can see where I'm pointing to. But you can also find the HSO3 very, very high up in the other side of the column. If it's on both sides of the table, that's what makes it amphoteric. So we actually have to use the 1.4 times 10 to the minus 2 number as the acid we divide by. And I ended up getting 7.14 times 10 to the minus 13. That would be this guy's Kb value. So is this thing going to be an acid or a base? It'll be an acid, yeah. Although the acid is not a very good acid, the base is even worse. And you may even be able to predict that by looking at the table. I would have told you guys a long time ago in your book to kind of maybe write something like these are your strongest acids going down to weak acids. And these guys are your strongest bases going up to weak bases. If you find where these things are located, the HSO3 is, yeah, it's pretty crappy on the acid scale. Does that make sense? But comparatively, the HSO3 on this side right here is almost all the way at the top. And keep in mind, these are the strong acids, these are the weak bases. This guy is almost the weakest base out there. The only weaker bases than HSO3 would be HOOCCOO, and the only one weaker than that would be water, which we probably know, right? Water can act as a base, but it does it 2 times in a billion. So as bad as this guy is as an acid, it's actually a better acid than a base. So the thing I need you guys to remember then is when you do your Kw divided by Ka, when you look up the acid value, leave it, that's fine. But when you look up the base value by dividing it, do not divide by this number again, because this is the guy acting as an acid right here. But this is the guy as a base. We need his acid on the other side's number. We need to use that guy's number that you divide by. That's all I got. You guys want to try one more example of that? Or do you feel like you got the hang of it? You good? Today's a pretty heavy lesson. Like, there's a lot that you can learn from this one here. The 2 main concepts are, I need you to be able to combine an ice table now, along with acids and bases, and use a Ka value out of your data booklet. Kids struggle with this so much, I find, on the diploma, because they forget that they have a Ka data booklet. They forget that they can't just negative log numbers just willy-nilly, right? You have to negative log an H3O. And then the other main thing we learned here is that we now have a way of telling whether or not an amphiprotic species is an acid or a base. You got to compare the Ka and Kb values. Whichever one's higher, that's the one it is. Okay. Questions, comments, concerns, conundrums, curiosities, complaints, criticisms, critiques? You're good? Okay. We don't have a ton of work days scheduled in here. Not that I'm assigning you homework over the weekend, but it wouldn't hurt if you at least start looking at your assignment, because we are 1 lesson away from being done the unit, just so you guys are aware. So Tuesday we're going to do a lab. Wednesday we'll do a quiz, and then Thursday next week is our last set of notes. Sound good? Go.